Hello and welcome. My name is Patrick Tshala. I'm going to go through fixed point binary numbers with you in this video. The content of the video is now displayed there. Have a time to, if you want to pause it to go through and see what is going to be covered in this video. Now, we've done some video where we have actually represented and worked with mostly only whole numbers. We've used both signed and unsigned numbers. Digital systems and computers do operate on both integers and fractions. The two commonly used number systems that can be used to represent numbers with fraction parts include fixed point binary numbers and floating point binary numbers. Now, the fixed point it says the binary point is fixed. In the floating one, the binary point floats. If we had, or when we use decimal, we call that point a decimal point. When we have binary numbers, we do call that a binary point. This video is going to cover fixed point binary numbers. Fixed point binary numbers are really similar, very similar to decimals. That means that some bits will represent the integer part and the rest will represent the fraction part. We have an example there showing a binary number with integer part and fraction part. We also have a binary point displayed there, and this is normally used here just to make it easy to visualize what we are talking about. In real life, when you use binary numbers, there is no symbol that can be used explicitly to store that binary point. There is also no way of knowing the existence of the binary point. It's only when you read the question or when you work with fixed point numbers, you'll have to agree on where to place the binary point. When converting decimal to fixed point binary number, it's really vital to understand how place values work. Let's actually take really this in practice and show how to convert or to represent 13.375 decimal using 4 integer bits and 4 fraction bits. We do start with, as we've done before, with place values. We put in our place values. Note that we do have what we've done before. From that point going left is place values for the integer bits. So that will make up the integer part. From that point going right will actually be are the place values for the fraction bits. That the bits there will actually make the fraction part. Note that we have other notation. We can use the base 2 using the 2 to the power of something, as we've done in the row number 1. Row number 2 is using fractions, which is equivalent to the row 1, or we can also use the decimal fraction, which is in the row number 3. Now, having our decimal places, we can then write and go to find where our binary digits will actually go. Now, note that we do need 13 integer part and 375 decimal part. Now, to come up with that one, it's really as easy as finding what are the decimal, what are the place values that will actually make us that number. So we can have an 8, 4, and 1 for the integer part. For the the remaining part, which is the fraction part, what we need to do is what are the position that we need to come up with 375. Now, this is now going to show you in full. In this case, we do need 0.25 and 0.125. This will actually make our fraction part. Now, this is done. We do have our value which we started off with, decimal part, which is there, and its equivalent, as we've worked out, is that. It's really straightforward, as easy as that. You can then verify your answer converting this back. You know that you see that this is how it works and this is correct. Take time to pause the video and then do the conversion. Express the following base 10 number in 16-bit fixed point sign magnitude format. Remember, when you see something that like this one, it's clearly giving you a hint of how to go with the conversion. If there's nothing like this one, if it doesn't say that, or it doesn't, it should actually say something 2's complement. Now, having, if you don't have anything saying like sign magnitude format or 2's complement, what it means is then in that condition you will be working with only unsigned value, but in this case it is sign magnitude format. Take time to do the conversion. In a while I'm going to show you the answers. Okay, remember that when you work with fixed point numbers, there is not a symbol to specify where the binary point is going to be. The question or the discussion will actually tell you where that is going to be. And in that question, we had clearly information telling us that we will be working with 16 bits number, which will contain 8 integer bits and 8 fraction bits. Now, to make life for us, we can then just put them there when we do the conversion. This is the answer. Take time to check it. If you've got the same answers, that's really well done. Keep up the good work. If you haven't got the same answers, so some of them, if they're not the same as what is displayed here, please, in the following second, I'm going to show you how we ended up with these numbers. Right, let's take the first one. The minus 13. What we have here, I'm showing you, we are using sign magnitude format. Now let's have the conversion. We do have the integer part as displayed there, all in red, 8 plus 4 plus 1, and then the fraction part, which is in blue, highlighted in blue. Note that with sign magnitude number, the leftmost bit indicates the sign, with a 1 indicating that it is a negative number. When converting 7.510 decimal, it also told us clearly that we use 4 integer bits and 4 fraction bits. We do the conversion with place values as we've done before, and then we go through to see that where to put the one, what do we need to have to make up the 7? So we need 4, 2, and 1. That should give us the 7, which is the integer part. The fraction part, we do need to come up with 0.510. Now, the corresponding values we have in for the fraction bit is actually here. Now, if you do the conversion of this back to decimal, you see that we lose precision. So instead of having 7.510, we do have only 7.5, because what is happening here is that there are infinite number of fractions, but there are only limited number of bits to represent them. Now, the first digit after the binary point is worth 1/2. The same thing in decimal. In this decimal system, the same digit is worth 1/10. Now, when you have the same number of digits in both number systems, decimal and binary, now when you have that number after the point, it means that the binary is less precise because it does not actually have those specific uh, value that corresponds back to the value in decimal. Let's now do the conversion from binary to decimal. We take that this binary number, which we are going to convert to decimal, and in this case we use 4 bits after the point. Again, we start with place values. Now, we do make it also clear, and every single question, whether it is exam, whether you're working with this in a different context, it will always tell you where to place the decimal points. So, sorry, not decimal point, because now we are working with binary, where the binary point will actually go. Now, in this case, we do have 4-bit fraction part, which we do have there. And the remaining on the left is the integer part. And again, we write the number to be converted. We then go to do the calculation. Now for the we do have this one split so that we can see what gives us what the integer part is and what the fraction part is. So doing the calculation, this is the result. Now pause the video and convert the following. 2's complement binary numbers to base 10. Now with this one, make sure that, in fact, we do assume that we have 4 bits after the point. Okay, now you can pause the video again to have a look at the answers. If you've got these answers, this is well done. Keep up the good work. If you haven't, I'm going to cover some of the numbers, how we have actually calculated them. Starting with the first one here, as you can see, the answers are there. Now the details are in this section. This is how it is done. We have actually started with the place values. We've written the number to be converted. And then from there, we have done the calculation. Notice now that when you use 2's complement, the leftmost bit has a value which is negative. That's what we have there. When we go with the other stuff, the other numbers, 1111.1111, the answer is that we are going to use place value. That's the method we use in that one. Again, as I said it before, with 2's complement binary numbers, the leftmost bit has a negative place value. That's the -8 we have there. When we do the calculation, this is the actual result, which is this. That's it. We take the 1000 0.0000, which gives us minus 8 in decimal. But again, using place value, with 2's complement, the leftmost bit, which is in that one, which is the MSB or the most significant bit, has a negative place value. That's where we've got the minus 8. The second method is going to show you um, the conversion, but going through the positive number. Now, when we start with 1111.1111, we are actually sure that since this starts with a 1, it must be a negative number. What we do is we convert it to a positive number, and then we convert that to a positive binary number. We calculate its positive equivalent in decimal, and then from there we work out the final negative in decimal. So doing that is we proceed by flipping all the bits and adding a 1 to it. Now, when you flip all the bits, it gives us 0, 0 everywhere. We add 1. We end up with that. Now, with that number, when converted, which is now positive, when you convert it to decimal, it will give us that value. Now, as it is decimal, which is positive, to make it negative, it's really easy. It's just by adding minus in front of it. With the 1000 and 0000, again, we do the same thing. We use as a two complement. In fact, what we do is we flip all the bits and then add 1 to it. Anything that was 1 becomes 0. Anything that was a 0 becomes a 1. Exactly the same as we've done in the previous one. Now, we've actually done a coverage of fixed point binary numbers, and we are going now to end with this video with a note on the advantages and disadvantages. What is really considered as an advantage for this the fixed point number is that it makes arithmetic much simpler, which is also influencing the processing. So the processing is actually faster. A notable disadvantage of fixed point notation is that it is of limited range. So that means that when you increase the number of bits after the binary point for precision, so you can increase it to get precision, but that also affects so that it decreases the range, and the other way also is true. Now, thank you again for watching this. If you have any questions, do not hesitate to contact us. We'll be happy to come back to you with your specific queries. Thank you very much. Merci beaucoup. Kiitos paljon. Tuossa Matondi mingi. Thank you.